discuss effect of sodium on the interaction of sulfur dioxide and calcium oxide. It's by R.B. Srivardhane and James Cook from Department of Energy and Mechanical and presented by Dr. Srivardhane.
The title of my presentation is Effect of Sodium on the Interaction of Sulfur Dioxide with Calcium Oxide. Various pollutant gases such as sulfur dioxide are produced during the coal combustion process. Limestone and dolomites are introduced to the combustors to remove these gases from the combustion stream. Calcium oxide is the major active ingredient present in dolomites and limestone, which is responsible for the removal of sulfur dioxide. Alkali containing material which are present in the effluent stream can condense onto the calcium oxide surface, and also the sodium in the bulk of the material can segregate to the surface at elevated temperatures. Therefore, it is important to study how sulfur dioxide interacts with sodium deposited on calcium oxide. The outline of the work that I will be presenting here is first the sodium evaporations on single crystal calcium oxide, then scanning OJ mapping analysis to see how the sodium is distributed on the surface, then scanning electron microscopy to see the changes in surface morphology, then finally to identify the chemical state of sodium by X-ray photoelectron spectroscopy. Then sulfur dioxide exposures on sodium deposited on calcium oxide, then identify the chemical state of sulfur. Then the reactions were carried out as a function of sodium to calcium ratio and also at three different temperatures, 373, 473 and 673 K. And then finally, the sticking probability calculations. The major technique that we used was X-ray photoelectron spectroscopy or XPS. The system that we used was VGSK3. It has two components, preparation chamber and the detection chamber. Sodium was evaporated onto the sample in the preparation chamber and was moved to the detection chamber for data acquisition. Using the XPS data, we can obtain the binding energy of different elements present on the surface. Using the binding energy, we can identify the different elements, and also it gives the chemical state of the elements on the surface. And peak intensities give quantitative measurements. Now let's look at the sodium evaporation data on calcium oxide. Now here the binding energy of the sodium deposited on calcium oxide are listed as a function of evaporation time. There was an increase in sodium coverage with increasing evaporation time. However, the binding energy decreases with increasing evaporation time. So this indicates that the first few layers of sodium may be interacting with calcium oxide surface and by donating electrons. That may be the reason for the higher binding energy at lower coverages. Now, in order to identify the form of sodium present on the surface, we compare its binding energy with standard compounds containing sodium. Now, as you can see, it's very difficult to distinguish different states of sodium based on the binding energy. For example, metallic sodium has a similar binding energy as sodium oxide. To solve that problem, we calculated the OJ parameter of the sodium compounds. Now, the OJ parameter is defined as the kinetic energy of the photoelectron peak minus the kinetic energy of the X-ray induced OJ peak. Here the kinetic energy of the sodium peak is plotted as a binding energy, function of binding energy of sodium peak. Now the OJ parameter are shown in the diagonal lines. Now as you can see, we can identify different sodium compounds using the OJ parameter plot. Metallic sodium is located in this region, while the sodium +1 states are located in this region. The open circles going from 1 to 5 are for increasing sodium evaporations on calcium oxide. As you can see, at high sodium coverages, the evaporated sodium as OJ parameter closest to sodium silicate. Sodium silicate was the compound used in the evaporator to evaporate sodium onto calcium oxide. However, silicon or oxygen were not detected on the calcium oxide surface after the evaporations. These are the scanning OJ maps, and this is for low sodium coverage and this is for high sodium coverage. The light dots indicate where the sodium is present. As you can see, sodium is randomly distributed on the surface at low coverages, while it is evenly distributed on the surface at higher coverages. Scanning electron photomicrographs are shown here, and this is for pure calcium oxide and this is for sodium evaporated on calcium oxide. There is a drastic change in surface morphology after the evaporation of sodium on calcium oxide. Now let's look at the sulfur dioxide exposures on sodium calcium oxide. When pure calcium oxide and sodium evaporated on calcium oxide were exposed to sulfur dioxide, we observe only one sulfur peak. Now this is for pure calcium oxide and this is for sodium on calcium oxide. As you can see, the binding energies were similar in both cases. So this indicates there is only one form of sulfur adsorbed on calcium oxide and that is not affected by the deposition of sodium. However, the intensity of the sulfur peak has increased tremendously on sodium calcium oxide system compared to the pure calcium oxide system. Now in order to identify the form of sulfur on sodium calcium oxide, we compared its binding energy with standard compounds containing sodium. Now this is the value we observed in our work, sulfur dioxide sodium calcium oxide, that's 167 eV, and that compares best with sulfide. Fission-sorbed sulfur also has a similar value, but it's not possible to have fission-sorbed sulfur at temperatures around 373 to 673 and after outgassing at 10 to the minus 9 torr. So sulfide seems to be the most possible form of sulfur present on sodium calcium oxide system. Now here the intensity of the sulfur peak is plotted as a function of exposure given in Langmuir's at 373 K. Different sodium to calcium ratios are listed here. Now as you can see, there is a rapid increase in sulfur intensity initially for all the sodium coverages and then it reaches the saturation value. It's also important to note, with increase in sodium coverage, there is an increase in saturation sulfur intensity. Here again the intensity of the sulfur peak is plotted as a function of exposure at 473 K. Again we see an increase in saturation sulfur intensity with increasing sodium coverage. Similar plots at 673 K are shown here. Again we see the same trend, an increase in sulfur intensity with increasing sodium coverage. So at all three temperatures, sodium somehow enhances the reaction between sulfur dioxide and calcium oxide. Now using the intensities of the sodium peak and the saturation intensities of the sulfur peak, we calculated the number of sodium atoms deposited on the surface and also the sulfur dioxide molecules absorbed at saturation coverage. Several important things can be noted here. There is an increase in sulfur dioxide absorbed with increasing sodium coverages at all three temperatures. However, the saturation sulfur dioxide absorbed at saturation coverage decreases with increasing temperature. sulfur to sodium ratio decreases with increasing sodium coverage. For example, for low sodium coverages, sulfur dioxide molecules absorbed is greater than the number of sodium atoms present on the surface. But at high sodium coverages, the number of sulfur dioxide molecules absorbed is less than the number of sodium present on the surface. And that's observed at 473 K. In this work, we used calcium oxide 100 surface. If you assume that the surface resembles bark, then the calcium 100 surface should have 8.6 times 10 to the 14 oxygen atoms per centimeter square. And that value is very close to the value of the number of sulfur dioxide molecules absorbed at high sodium coverages. Even though the number of sulfur dioxide molecules absorbed does not correspond to the number of sodium atoms present on the surface, it's equal to the number of oxygen atoms present on the surface. Now let's see how the sodium could activate the calcium oxide surface. As we saw earlier, sulfide was the form of sulfur absorbed in the sodium calcium oxide system. Now, in order to form sulfide, it should utilize oxygen from the calcium oxide surface. At high sodium coverages, sodium has activated all the surface oxygens to form sulfide. Now, there are two ways how the sodium could activate the surface. One way is to form a bond between sodium and oxygen and to participate in the reaction to form sulfide. The other way is to activate the neighboring sites. Previous workers have observed that sodium could activate various catalytic surfaces for different reactions. And this activation has been attributed to the electron donation activity of the alkaline material. Now finally, the sticking probability calculations. Coverage theta and exposure L are related to sticking probabilities as seen in this equation. Now if we assume that there is a first order absorption with no precursors, then S should be equal to S0 times 1 minus theta, where S0 is the initial sticking probability. If we combine the two equations and integrate, we get this form of equation. Now if you plot log of 1 minus theta versus L, we should get a straight line if our assumptions are correct. And from the slope, we should be able to calculate the initial sticking probability. Sodium to calcium ratios and initial sticking probabilities and F, that's the fitting parameter for the log of 1 minus theta versus L plot are listed here. Now as you can see, at both temperatures for all the sodium coverages, the fitting parameter is greater than 0.9, and this indicates that the log of 1 minus theta versus L plots are linear, so that assumptions of direct one-sided absorption may be correct. The initial sticking probability decreases with increase at low sodium coverages. When sodium is deposited on calcium oxide, there will be two things will happen. As we saw earlier, there is activation of the surface by sodium. At the same time, the accessibility of the active sites may be diminished in the presence of sodium. Those two things may be controlled in the initial reaction, and that may be the reason for the decreasing initial sticking probability at low sodium coverages. Finally, the conclusions. Sodium was deposited on calcium oxide with sodium plus state, and scanning OJ mapping analysis indicated there was random distribution of sodium on the surface, and scanning electron microscopy showed there was a drastic change in surface morphology after the sodium deposition. There was an increase in adsorption with increase in sodium coverage. However, there was a decrease in adsorption with increase in temperature. Number of sulfur dioxide molecules absorbed was equal to number of surface oxygens, and sulfide was the form of sulfur observed on the surface. And sodium activated the calcium oxide surface with sulfur dioxide adsorption, and this may be either due to the formation of Ne or Ca bonds or due to the activation of the neighboring sites. Sticking probability calculations indicated that there was first order absorption with no resistance. Thank you.
Your study with the calcium sulfate, that was a single crystal study?
Yeah.
Would you expect with multi-crystalline body that you'd see sodium segregation at the brain boundaries for other systems, aluminum oxide systems? So
Yeah, there is a possibility, but if sodium sodium is deposited on the oxygen atom, so I don't know whether that could happen because mostly it's just due to the chemical bond.
Thank you. Yes, we're doing excellent time-wise, we're 10 minutes ahead. I'll go ahead with the next paper.